Good afternoon, everybody. Welcome to this week's Triangle Quantum Computing webinar series. I'm your host. My name is Eric Geisels. Today, I have the pleasure to host a webinar presented by Dylan Herman. Dylan is a quantum computing researcher at the JP Morgan FLAIR lab, which is the future lab for applied research and engineering. I must admit, it's a very nice acronym. He has a bachelor's degree in electrical and computer engineering and computer science from Rutgers, and has been with JP Morgan since 2018. He's going to talk about HHL, which is referring to a paper 2009, if I'm not mistaken, by Harrow, Hasidim, and Lloyd. So we're talking about linear algebra. That paper kind of established that we can get up to exponential speedups for standard linear algebra operations such as inversions of matrices. Those things have proven to be challenging with the current hardware that we have in quantum computing. And the nice thing about this paper is that it's putting us in the NISQ area, HHL. So Dylan, I'm looking forward to your talk. This looks like great stuff. So it's all yours.
Thank you, Eric. So hi, I'm Dylan, and today I'll be presenting our work titled NISQ-HHL. So NISQ is Noisy Intermediate Scale Quantum, Portfolio Optimization for Near-Term Quantum Hardware. And so this was done in collaboration with a few of my other colleagues, Romina Yelovetsky, Pierre Minson, and Marco Pistoia. And we're all from the Future Lab for Applied Research and Engineering, FLAIR, at JP Morgan Chase, and which is led by Marco. And so the preprint archive version of this paper is online, as well as it was also presented at the American Physical Society March meeting. Just a little bit overview of the FLAIR program. So FLAIR is JP Morgan Chase's research lab, and so we focus on frontier technologies. One, of course, is quantum computing. The other is quantum communication. So in that area, we're investigating things like quantum key distribution, which is popular for establishing symmetric keys, which can be used for securing high confidential data and ensuring confidentiality. And so that's generally our quantum technologies area. We also have augmented and virtual reality. So we're developing additional usable tools for consumer banking, and for also, we need to ensure security as well, so that whenever using virtual augmented reality, there's security included, Internet of Things, and then blockchain cryptography. So in blockchain cryptography, one important part is because quantum computing will break public key cryptography. We also need to potentially look at alternatives like post-quantum cryptography, and also ways in which we can ensure confidentiality with quantum key distribution. So just an overview of the NISQ-HHL presentation I'll give. So this paper introduces NISQ-HHL, which was an extension of this classical quantum hybrid version by a group under Lee et al. And so this algorithm was designed to try and not necessarily get the full speed of HHL, but be able to execute some simpler examples, or to actually even get any benefit in the near term of running it by splitting up HHL into multiple blocks that we can run on a quantum computer, but also utilize classical computing to better to combine the results from multiple circuits. And so, as mentioned, we're applying this to portfolio optimization. So Reventros and Lloyd, a couple of years ago, established that HHL could be used for solving a certain portfolio optimization problem. And so for our work, we decided to apply NISQ-HHL to this to see if we can run larger experiments than could be done with the standard HHL on current hardware. So we executed this on the Quantinium system model H11. And so Quantinium, formerly Cambridge Quantum, formerly also Honeywell Quantum Solutions, which are now merged. So this was originally the Honeywell device. And this is a trapped ion device, which at the time had around 10 qubits. And one of the benefits is that it supports current hardware features that at the moment, no other hardware supports all of them. So mid-circuit measurement and reuse, which was recently also added to the IBM device, but also quantum conditional logic, which is very important for this algorithm to be able to work. And I'll get into what those mean. And then also we developed a novel algorithm for scaling of the spectral norm, because with HHL, it's important that the eigenvalues lie within a certain range. And so this algorithm allows us to effectively determine this spectral norm. So just start with the portfolio optimization problem we looked at. So this is known as the Markowitz portfolio optimization. This is very common simplified formulation. So here we start with a convex quadratic program. So here we have the quadratic form here, which is defined by our weight vectors, and also our correlation or covariance matrix, which is based on historical data. And our goal is to minimize this, which is effectively minimizing our risk. And in this case, we also include two constraints. One is for the budget. So we have the prices of the various assets. W is the proportion in which we're going to invest in each asset, and also can include whether we're going long or short. We also have this mu over here, which is our desired expected return. Certain other formulations that are popular for solving quantum computing are the combinatorial formulations. So you'll see where instead of selecting a proportion of the portfolio, we'll select whether to buy or sell an asset or include an asset in our portfolio. And so that typically is an NP-hard formulation and utilizes techniques like QAOA or quantum annealing. But here we have a convex version. And here, because it's a convex quadratic program, we here apply the method of Lagrange multipliers and end up with a linear system of equations. So this is at the cost of introducing two extra parameters. So we have Lagrange multipliers, one for each constraint. And this now reduces to solving a linear system. And even though this problem is efficient to solve classically, potentially with HHL, we can still get a further speed up because it does allow for solving certain linear systems problems exponentially faster. And so our goal will be to run this with HHL. So here we'll be formulating portfolio optimization as a QLSP. So QLSP stands for Quantum Linear Systems Program problem. And so this was the problem that was developed alongside the development of the HHL algorithm. And so it is known to also be a BQP complete problem. So all polynomial time quantum computing can reduce to sparse matrix conversion. And so what this problem allows us to do is that we take the original linear system and we convert it into a quantum linear system where when we invert the matrix, what we're going to get is a state that's proportional to the solution of the original linear system. And so here we have B, which is the vector in the range. And so this consists of our Lagrange multipliers and so on after the constraint, but also go back here, we have 0, which is related to when we take the derivative and use the Lagrange multipliers, we have the right side as well, 0 vector here. And so this is a very efficient vector to be able to load because we really only have two non-zero values and the rest are these 0 vectors, which would be a simple rotation. And so what HHL does is it produces the state which is proportional to the solution. And so here it's represented by B and inverse A. And because HHL was originally designed for Hermitian matrices, you can also do variants in which you can deal with non-Hermitian matrices, non-square, and so on, like singular value estimate decomposition. But here, because it's Hermitian, we can decompose it into a orthonormal basis of eigenvectors. And effectively what happens is that B can be decomposed into this basis. And then the inversion consists of inverting the eigenvalues here. And so this can be done using HHL. And it's well known that HHL has a few caveats associated with it. One is the sparsity. So because HHL, the original HHL formulation, which has been improved significantly, but it originally depended quadratically on the condition number. So condition number is the maximum singular value of a smallest singular value or eigenvalue in this case, or magnitude of eigenvalue. And it needs to obtain the speed up because we're looking for this exponential speed up. It's ideal that the condition number be polylogarithmic in the dimension. However, in this case, we'll see that's not going to be the case, but that's really ideally what's needed for the HHL speed up. And so, however, in this case, we're dealing with a classical problem where we just having the quantum state is not enough for us. We need to be able to interpret the portfolio somehow, which is to store in this quantum state, which if we were to perform a measurement, let's say the computational basis, we'd randomly get a basis state with probably proportional to the weight in which we're investing. And that weight is what we actually need. So one potential way is to perform tomography in which we obtain the full state vector that would kill the exponential speed up. There are certain efficient tomography techniques like the L infinity tomography technique, which does have sort of an exponential speed up. However, there's other things we can do without reading out the full state. So one is if we have a candidate portfolio, for example, a portfolio manager has and wants to compare whether it's how close it is to the ideal portfolio produced by HHL. It's very efficient to compute inner products in quantum. So you can take this portfolio, load it onto a quantum state, and perform what's known as the swap test to compute the inner product, and then the inner product will be 1 if they're exact, and so on. In others, if the solution is sparse enough, we can sample from it. So if the overall solution is sparse, we can, it's effectively performing tomography in a sense, but there's not exponentially many non-zero values. And also in others, we can also measure certain observables. So for example, an example of observable is the covariance matrix. So we can determine the risk associated with our portfolio. And so there's a variety of things we can do with the HHL solution still, potentially obtain this exponential speedup. So here, the first thing we utilized was we looked into how do we improve quantum phase estimation for the near term. So over here on the right, we have the standard quantum phase estimation. And the goal of phase estimation is that given an input eigenvector, you can estimate the eigenvalue or the phase associated with the eigenvalue for a unitary matrix. And in this case, the phase is the phase is the eigenvalue of the matrix we're inverting. And so if you look at the standard QP, what happens is that the number of qubits we need to estimate the precision of our eigenvalue scales linearly, the number of qubits scales linearly with that. So however, potentially we could require very high precision to represent these eigenvalues or to estimate them. So we need increasingly more qubits, which of course, NISQ devices don't have many qubits and they're very noisy. So we want to reduce this number of qubits as much as possible. So one thing that was noticed in a paper by Griffiths was that if we look at the first qubit here on QP, we're effectively performing a simple Hadamard test in which we're going to measure the last bit of the eigenvalue, the least significant bit. And there's this principle called the principle of deferred measurement, which says that the measurements here actually commute with the controls. So what happens is this qubit isn't operated on anymore. So we can actually move this measurement forward, which is what we get is called the QCL-QP. And so here effectively we've reduced QP that requires 3 bits for 3-bit precision to one that requires a single qubit, but uses something called quantum conditional logic and mid-circuit measurement. So here we'll see that these measurements, which originally were at the end, are now in between qubits or in between gates. So here we're effectively performing the estimation of the least significant bit first. We then have here this 0, which is a ground state reset, and ground state reset allows us to reuse this qubit for estimating the next bit in the eigenvalue. So the depth of the circuit is still the same compared to the original QP. However, now we no longer have extra qubits, which of course is costly. And so this observation comes from also that the output of the Fourier transform, which is we're effectively when we're forming QP, we're constructing this state. And here these J's correspond to the bits of our eigenvalue. And we perform the inverse quantum Fourier transform, which gives us the eigenvalue in our quantum register, which we can then measure. And so effectively each one of these powers of U's here, we see are constructing these parts of the product state. And so here we could effectively measure each bit one by one and reuse the qubit to measure that's used to estimate that bit. And so as mentioned, what we now have are, instead of 2 qubit gates, which are very noisy on current quantum devices, we've converted them to single qubit classically conditioned gates. And so we can, on the Honeywell device, we can store the measurement and later on have a kind of if then else logic, which will apply this gate depending on the measurement result. So to better understand how we can actually apply this to the HHL setup, and in the HHL setup, we don't actually just have an eigenvector, we have an input that's a superposition of eigenvectors. So what we need to understand better what happens in the case of a superposition of eigenvectors. So in this case, we have the original QCL-QP circuit. And here in step 1, what effectively happens is that we're measuring the least significant bit of the eigenvalue. So the input vector is some arbitrary superposition of eigenvectors, and each eigenvector has some sort of eigenvalue. Yep.
Yeah, there's just perhaps a simple clarification question. If you check on your chat by drawer, Baron, could this trick of moving the measurements based on be used also for NISQ version of quantum Fourier transform, QFT?
Yeah, so it can be used for implementing that's like, well, what it's doing here is actually implementing a NISQ version of the inverse quantum Fourier transform, because in the end, you're still measuring at each step, and then you're going to end up, so if you have a superposition of eigenvalues, you're going to only end up getting one of them at each measurement. So that's exactly what we're doing. We're using it to implement a NISQ-friendly inverse Fourier transform, but not the original Fourier transform. So nothing that requires coherence.
Thanks.
So here is what we do when we have multiple superposition eigenvalues. So this B is the right-hand side of our linear system of equations. And so the first step here, which is 1, which is showing what the output of the quantum state is. So here, beta here is the amplitudes in the linear combination of, so B is a linear combination of these U's, which are eigenvectors. And we perform this simple Hadamard test. We end up getting this superposition here, in which some of the eigenvectors may have eigenvalues that have a 0 bit is least significant in binary, or, and it assumes we have finite precision. Of course, if it's infinite, we need to truncate at some point, but this is assuming we have enough precision to represent these eigenvalues. And the right here, this is the ones that have a 1 bit. And so effectively what happens is when we perform this extra Hadamard, we're measuring the X basis. And what the X basis will do, we'll end up either measuring this part on the left or this part on the right, and we'll collapse the state to either one of them. And in 2, we'll end up with either a superposition of all eigenvectors that have eigenvalue with least significant bit 1 or with 0. And so that's what this J apostrophe means, is basically that we're getting one of these measurements randomly. In the next step, we need to measure the second bit. So here in step 3, what happens is we get this state, which is now, instead of getting the last bit, we shift one less. So now we have the last 2 bits. And here we get a superposition over the eigenvectors that had J1 as their last bit, but also the ones that have a 0 in the second last bit or a 1 in the second last bit. And the problem is this is no longer a single bit estimation. We now have this extra factor here that we have to correct for. But luckily we measured it in a previous step, so we know the result. And because we collapsed to one of these states, we can now use this, perform this gate, this rotation gate, which will subtract this J1 depending on our measurement result. So if it's a 1, we need to subtract J1. To 0, we do nothing, because now it's just a single bit of information. And so in 4, we get what happens when we subtracted, and now we have another single bit QPE or Hadamard test. So effectively, you can view it as kind of like a binary tree, where each step we're making a decision projecting onto a 0 or 1 bit on each bit. And what this allows us to do is repeating it multiple times. If we have a superposition of eigenvectors, we're going to get the same distribution that we would have gotten if we performed coherent original QPE, but it constantly just measured. So we lose coherence, but we get this distribution of eigenvalues. And so the second step, we use this to help solve is known as the eigenvalue inversion, which is an important part in HHL. And so we'll see how we actually use this to as a component of this. So in eigenvalue inversion, what happens is that, so first we performed we have a linear combination of B is a linear combination of eigenvectors, like we saw before. We perform quantum phase estimation, which now in a second register performs and has an estimate of the eigenvalues associated with these eigenvectors. And the goal in HHL is to take these the estimates here and rotate them onto the amplitudes, or the inverse of them. Because effectively what we want is we get a superposition over what we desire and what we don't desire. So this 1 over lambda is effectively the inversion. So we want the component to the right of this plus sign. And so effectively with HHL, you have to measure a few times, and with a certain probability, you'll get the desired result. So this inversion step here is what we're going to try to improve, because to do this, you originally needed the coherent phase estimation, which is mentioned, the number of qubit scales with the precision. So there's a technique that the hybrid helps us with. But typically in the NISQ, so if we, outside the NISQ era, we can do this operation with quantum arithmetic. So typically we can compute the arc sign of this value into register. And then once you have the arc sign into register, it's very easy to perform this rotation. Unfortunately, quantum arithmetic is very expensive on this devices, and to some extent is impossible. So for now, typically what we do is we have, it's called this uniformly controlled rotation, which is one simple technique for the NISQ error that is, it scales exponentially, but is possible in NISQ error. So here we have is a uniformly controlled rotation is a single gate, multi-control gate that decomposes into for n control bits to the n rotations. And so effectively what it does is it controls on all possible estimates in the this register T. And excluding 0 because we can't invert 0. So this is starting with 1, 2, and so on up to the n minus 1. However, if we need n bits, this is to the n gates, which has become very expensive. And also it's multi-control gates, which we need to decompose them into 2 qubit gates and single qubit gates, which can blow up. So, and there are other alternative techniques as well for this, but we focus on the uniformly controlled rotation, and we'll compare NISQ-HHL to that. So for NISQ-HHL, we utilized an extension of the Lee et al. Hybrid technique. So here we start off with QCL-QP, which in this case, that's the version that uses conditional logic. And here what we end up doing is just estimating the eigenvalues because we don't do any inversion yet. We just need estimates of the eigenvalues. And so what happens here is by repeating this process multiple times, we'll get a distribution of eigenvalues who, if we look at the input vector B, which is the right-hand side of the linear system, if we decompose it into the eigenvectors of A, we'll get the eigenvalues whose eigenvectors have non-zero coefficient in that expansion. So we want us to get all eigenvalues, but only ones that are relevant. Now, the one issue here is this is immediately where the HHL exponential speedup goes away. Because now we're performing some sort of classical post-processing. And in the worst case, the n by n matrix can have n distinct eigenvalues, which now are performing n operations. But also this post-processing involves looking at all the possible outcomes anyways, which is exponential. However, the goal is that this is easier to run on near-term hardware and also potentially provides benefits in practice, which as we get larger scale computers, we can compare this to the original classical linear systems. So now that we have these eigenvalues, we can perform classical post-processing to improve this inversion technique. So here we define what we call the relevant eigenvalues. And if we look at this distribution, the probabilities associated with each eigenvalue estimate here are the magnitude of these beta i's, which are the coefficients in the expansion of B in eigenbasis A. And we also have estimates of the eigenvalues. Thus we can compute 1 over that estimate. So we want to process or only consider inverting the ones that A, the value beta is high, and B, 1 over epsilon is high. So a small eigenvalue can end up having a large 1 over epsilon. But we also want to make sure we have a certain cutoff to deal with the conditioning problem. But this allows us to now perform this post-processing. And from here, we run the original HHL algorithm, which, however, we don't have to use this uniformly controlled rotation. But we can cater these rotation gates based on our estimates.
Can I ask a quick kind of adversarial question?
No, please.
If you were to have a case in the parameter space, if I can use that word, of betas that are proportional to lambda, beta I proportional to lambda I, I'm creating this adversarially, keep that in mind. You're kind of stuck here, right? Because you're not going to get that threshold. I can create it proportionally that they're all equal and necessarily I can scale into anything. So you're looking for a spiked case essentially, but not all cases may be like that.
Correct. You could end up having, yes, there could be a case in which it's now either uniform, they're all important, in which case you have to process all them. This is, yes, it's a technique that does have caveats, and it could be, you could have in effect having to deal with all these inversions. So that is correct.
Yeah.
This is one potential post-process technique, and also choosing this epsilon can be tricky.
Yeah.
But yeah, that is true as well.
Sure. Sorry to interrupt you.
No, please. So in the step C, now we originally run this original HHL, but now these rotation gates are only the ones in which the eigenvalue just have to invert on. However, even if we had to invert on all possible eigenvalues of A, it's still the uniformly controlled rotations can still result in more rotation gates applied, because if you look at the number of rotations depends on the precision, not the number of eigenvalues. So potentially require high precision, and this QCL-QP allows us to use the high precision with that increasing number of qubits by a lot. And so now the number of rotations only depends on the dimension of A as opposed to the precision. And so also in this last HHL step, we can actually, the goal of this QP, which is now the coherent one, this is no longer the QCL-QP with the mid-circuit measurement reuse and quantum conditional logic. Its goal now is it no longer needs to estimate the eigenvalues to high precision, but it needs to be able to divide the eigenspaces, which means we can use lower precision. And by dividing the eigenspaces, this allows us to effectively perform, we basically just need to know which rotation gates to apply to which eigenvectors, or eigenvalues. So this allows us to effectively have higher precision with QCL-QP, and then last step, utilize a low precision QFT, which also requires classical post-processing. So that's the general framework here. So the second algorithm which we introduced, which is part of this whole framework, but can also be used separately, is the Spectronorm scaling technique. So as mentioned, HHL requires a spectral norm, which would be the absolute value of the maximum absolute value of an eigenvalue, or a singular value in this case, but we have a Hermitian matrix. Needs to be less than 1 because with phase estimation, we need all the exponents because the eigenphase needs to be less than 1. So we need to make sure there's no wraparound. And the second is also, if we can scale the spectral norm to be not 1, but close to 1, what happens is that in our distribution of outputs, we effectively make better use of the precision we have, but also differences that are small between estimates become large. So to do that, we developed this technique where we effectively estimate the maximum eigenvalue. So, however, at each step, this QCL-QP is only considering if B is a linear combination of a subset of the eigenvectors, not all of them, and maybe certain eigenvalues aren't there. We're only looking at the maximum one in the decomposition of B. And so what this technique does is effectively start off with an overestimate. And when you overestimate the largest eigenvalue, what happens is effectively all of the estimates get crushed to 0 or close to 0, in which case we kind of have an idea that we've overestimated. And then next step, as we increase this factor, so effectively we're dividing by a smaller number, we spread out the distribution more. And then finally, we can eventually get a optimal scaling parameter in which we're able to, the maximum eigenvalue is as close to 1 as possible. And so I'll discuss these algorithms, but that's effectively what's happening in these diagrams here. And so here we have the first part, which is we'll call algorithm 1. And so this is where the actual scaling happens. So we have here where on this graph, here we have examples in the QASM simulator, so the quantum simulator, theoretical values of the eigenvalues, which were estimated using a numerical solver, and the H1 device, which is where we actually ran QPU on, which is the Honeywell device or the Quantinium device. And so in the second step here, we see if we get a better estimate of the scaling parameter, we can spread out the eigenvalues, and ones that were clustered together are easier to estimate. And so what happens here is we start with some initial overestimate, which we'll get to how that's computed or how we can kind of figure out that overestimate. In each step, we perform a QCL-QP, in which we estimate this distribution. Again, this involves a classical post-processing technique, which could be exponential, but we now effectively look at what is the basis state with the maximum probability, so we estimate the maximum probability. And if this is 0, this means we still are dividing by too high of a number. So with QPE, let's say we choose like n bits of precision. If all the information we have about the eigenvalues is not in that window, so we divide. So for example, if our eigenvalue is less than 1 over 2 to the n, we're going to see an estimate that's very close to 0. So what effectively happens is we perform bit shifts until we start to see an estimate that's non-zero in this distribution that has a high probability, which means we're getting closer to the maximum eigenvalue. And the maximum eigenvalue will be the one that kind of shows up first as we do this bit shift. And so this can be done with logarithmically many iterations. And so eventually what happens when we start to see an estimate that has a non-zero probability, that's non-zero and has non-zero probability, we know this is close to the maximum eigenvalue, we can scale this to be 1. And so that's effectively what this procedure is doing here. And it's using multiple iterations of QP. And once we have this scaling factor, we can now use it to perform HHL. And so, as I mentioned, we need to figure out how do we determine this overestimation. And so here, this overestimation is alpha. So we saw on the previous slide here, our assumption is that this lambda max, which is the one we're trying to estimate, when divided by this overestimate alpha is less than 1. And so our goal is to verify that this is actually a good guess. And so what this technique does is we perform a QP quantum phase estimation that determines if all the estimates are effectively crushed to 0. And again, by crushed to 0, if you look at, this is the distribution in which we're able to estimate certain eigenvalues. We divide by a very large number, the highest estimate becomes 0, and all the theoretical values here are concentrated around 0. And so our goal is that if it is an overestimate, so an overestimate means that when we scale by this number, all our eigenvalues are less than 1. And this means that if we have n bits of precision, and we divide by 2 to the n plus 1, which shifts all the values out of our range, we only have a precision up to 1 over 2 to the n, everything will be effectively crushed to 0, and not exactly, and it's not going to be exactly 1, but effectively crushed to 0. And this allows us to determine if this is a valid overestimate, and this process can be repeated. And so performing algorithm 2 allows us as like a heuristic to verify if the initial guess works. And then algorithm 1 works with, again, logarithmic many operations because we're shifting by n bits each time. That's increasing it by 2 to the n each time. And so yeah, so this is an end-to-end view again, kind of bringing up this graph. So just to so the first step A is in which we utilize this quantum conditional logic quantum phase estimation, in which we can estimate this distribution of eigenvalues, which is again where the difference between HHL and this hybrid version works. And this is similar to what the original work of Lee et al. Did, but here we don't need to use the standard phase estimation for this. We can use this QCL-QP version. And then once we have this distribution, we can perform certain classical preprocessing on it to then construct the HHL, the original HHL circuit that uses fewer rotations than this NISQ version, which has a rotation for all possible estimates. And the number of rotations is bounded in order by the number of eigenvalues the matrix can have, which for n by n is n, distinct ones. And that's actually the worst case for this algorithm, is that there are n distinct ones. But there are other cases as well. But in the case of the uniformly controlled rotations, the number of rotations depends on our precision. And we can also, because we're splitting it up into 2 steps, we can use a higher precision for the A and B parts. And the A and B parts are effectively determining these angles of rotation to perform the inversions. But the controls of the rotations, what the rotations are conditioned on, doesn't need to be to the same precision that the angles need to be. This is just so that we can, this QP here, which is standard, needs to be able to separate the eigenspaces with different eigenvalues. And so we can kind of perform a post-processing where we can figure out how do we map certain eigenvalues. So here, let me see that. Yeah, so here, if we saw in this last graph here, which was done after we did the scaling, we can see that the theoretical value here falls between 2 estimates. So effectively, a eigenvalue estimate in a higher precision, when we go to a lower precision, can be split across multiple estimates. So it's nearest 2 estimates. And those we can effectively control on, but we can use the same angle. And so, and then, the last step is then to perform the original HHL, which gives us that state. And then, so that's for the hybrid NISQ-HHL. So here are a few experiments on the phase estimation step. So the experiments that I'm going to discuss are based on a problem in which we try to solve a portfolio, a simple portfolio of 2 assets, which is already pushing still what NISQ devices can do. But this would be difficult to even run with the standard HHL, as we'll show. And then with this results in a 4x4 matrix, we have 2 extra Lagrange multipliers. So here, if we compare the standard QP and the quantum conditional logic version, what we did is for a varying different precisions, so 3 bits, 4 bits, and 5 bits, we estimate the number of gates, the qubits that are required. And this fidelity is the classical probability fidelity. So what we did is just you take the probability distribution, and you could use like different distances as well. With this one, we just chose the fidelity metric. And so this shows how close the probability distributions output on the hardware versus the simulator are. And so we see with 4 bits, we do get a higher fidelity with QCL QP. And then so for determining the rotation angles that we use in the inversion step, we can use this higher precision. However, as long as the standard QP is able to divide the eigenspaces properly, we don't have to use the higher precision. And so this helps us determine what precision is required for the next step, because we can perform this step before running the whole HHL. And then for the eigenvalue inversion experiment, so this is after we performed all the estimations, we have our distribution of eigenvalues, we classically post-processed all of these eigenvalues, and now we can run the inversion part. So here we did a comparison, again, with this portfolio with 2 assets part problem, and we compared it to the uniformly controlled rotations. So this is the one in which there's a rotation for each possible estimate. And then we utilize a swap test. So a swap test allows us to compute the inner product between 2 quantum states. And so we can take the solution we obtained numerically, load it onto a quantum state. And now that we have the solution from HHL in a quantum state, we can compute their inner product and see how close they are, which is one metric. And so here we have that with NISQ-HHL, even for the small problem, we have a higher overlap between the 2 states. And here the number of rotations did not drop, it only dropped by 1. However, there's a few things we can say about this. One is, of course, it's a small problem, and as you scale, this number here depends on the precision you're using, not the number of eigenvalues. Whereas here, this number 6 depends on the number of eigenvalues in the matrix. And also because when we're going from the first step using a higher precision phase estimation, the QCL QP, and the second step is potentially using a lower phase estimation, what happens is eigenvalues that we can distinguish properly in our distribution with the first step of the higher precision one may end up splitting across multiple estimates in the second. So we have to perform multiple controlled rotations for each one. So an eigenvalue which we don't have precision to distinguish can end up becoming 2 different estimates.
Can I ask a quick clarification question? This inner product, is that with respect to the known solution, which in this case is easy to compute?
Correct. Yeah, so we compute it with a numerical solver, and then you can, which is easy, you can compute it in float form too. And we load that onto a quantum state and then compare those to verify how close it is. You can also read out the solution too, but you can do this technique, and this is similar to where I mentioned if a portfolio manager wants to compare a candidate portfolio to optimal.
I understand. Thanks.
And then so in the last one we have here is in simulation. So in simulation, we tried to scale up this problem a little more because we can do more on the simulator. So here we tried with a problem with 6 assets and 14 assets. And so here we see a larger drop in the number of rotations. So here we have 64, 4 for NISQ-HHL, and 64 for uniformly controlled rotations. So even in simulation, this allows us to run larger experiments. And so, so this effectively shows that there is a reduction in the overall depth using this technique. And so so some conclusions are current limitations and future work. Some I already discussed. So one is there is no exponential speedup, because once you perform this intermediate step of classical post-processing, the exponential speedup's gone, because in the worst case, you have n distinct eigenvalues. And HHL, the goal of HHL is to run in polylog n. However, we need n time to process them in the worst case. And also this processing of distributions is also potentially exponential. However, there are cases in which the number of distinct eigenvalues can be small, which this can obtain some sort of benefit. But in practice too, potentially as we get larger scale quantum computers, we can benchmark this against classical solvers and see if there is any benefit. So this work is not claiming any asymptotic speedup, just showing a way to also potentially benchmark HHL in our on near-term quantum hardware. The second, which is a topic I kind of overlooked, was the Hamiltonian simulation. So at each step for phase estimation, you need to be able to simulate the evolution generated by the matrix A. So in this case, in our system, the matrix was Hermitian, so it can be used to generate a quantum evolution. And so to simulate this evolution, we need some sort of Hamiltonian simulation techniques, which are very difficult to run on near-term hardware. So potentially we could find some NISQ-friendly techniques. There is other literature in which found ways to use other techniques to actually implement this simulation. However, at the moment for our experiments, what we simply did was you compute the unitary and actually pass it to, let's say, Qiskit, and Qiskit will decompose it into gates. So this doesn't really tackle the full NISQ problem. It mostly focuses on the phase estimation and the inversion steps. So that's potential path future work. And the last is the condition number. So we did an experiment where for a bunch of S&P 500 assets, we try to see what was the scaling across multiple years, what was the scaling of the condition number. So as mentioned, the HHL scales quadratically in the condition number. Here, we're plotting the condition number versus the number of assets. So in this case, the condition number scales quadratically in the number of assets. So in the end, we would have something like n to the fourth. So one goal would be to try to apply preconditioning techniques to reduce this and potentially be able to make use of this algorithm, well, because it also kills the exponential speed in a sense. And so, yeah, so that's I have. Thank you. And please see the JP Morgan site for more information on there, and I'll take questions now.
Yeah, thank you. If you have questions, you can always use the chat. Can I get you onto the previous slide? The plot. So in most portfolio applications, I would expect the following is that you get a small number of dominant eigenvalues, and then the rest drops off to zero. That's kind of the factor model story. But that's going to have very little impact on the conditioning number. Am I right? As you expand the number of assets, because you just pile up small eigenvalues, and that doesn't change the spread between the smallest and the largest. Am I wrong on this, or do I misunderstand what's going on in that plot?
Oh no, so you can because if you have if your number of eigenvalues still remains fixed, you're scaling up the matrix. No, it would not affect the condition number in that sense. However, here in this case, we did see an effect, and we actually saw that there was. I mean, maybe because this was just the random data, but this was historical. Sorry, it was historical data, in which we did see there were a lot of non-zero or relevant eigenvalues. But that was also one argument which we've seen in literature is that there are potentially only like the covariance matrix is low rank, and we can actually use these. Yeah. So that's one argument, and we didn't see it here, but that's potentially the algorithm more useful.
Yeah, my suspicion is that you have a very noisy estimator of the covariance matrix that gives you this result. That's my suspicion. I mean, I don't. I would sort of perhaps think that might be the reason. I wonder. I know that you focused on portfolio applications for obvious reasons, given that you work at JP Morgan. But something called like quantum Gaussian processes, where there is a lot of linear projections going on, meaning you have to invert a lot of matrices for least squares projections. So that might be actually another direction to go with this, right? Or have you thought about other ones besides the one that I just mentioned, where HHL, the sort of implementation of HHL on NISQ kind of can make a difference?
So yeah, so I've seen some literature on that because because HHL can be used for that as well. So you can use it for Gaussian process regression and so on. We haven't actually thought about it, but yes, we could apply it for
Yeah.
as well as potentially other applications we could use it for.
So there are two questions in the chat. You can probably take a look at them, and everybody sees those questions, right? So there is one by Elton. Maybe I should slide up. Actually, let's take first the one by Thomas. So Markowitz problem is defined with non-negative variables. How you solve those? So that's a question about short sale constraints, essentially. You're coming up with a portfolio that potentially does not have short sale constraints. But that's another Lagrange multiplier, right? I mean, that's my guess.
So yeah, there is no non-negativity constraint added. You can add that as well. So it is allowing, and also in the initial formulation by Reverend Torsten Lloyd, they didn't add this. You can, in which case there have been techniques that use like second order Cohen programs and so on to solve it. But here we did not include for that. So we do have potential for negative, and in which case you would need to estimate the sign and determine for the short sale.
So the next one, there's quite a few messages. We're having fun here. Elton, practical portfolio optimization is much more complicated and is generally phrased as a mixed integer programming problem. I mean, there are many applications of that in quantum. Would this be applicable here or there? Why don't you go? I may have an answer to this too, but go ahead. Go ahead.
Oh yeah, so mostly like in the quantum literature I've seen, there's of course the ones that focus purely on the integer programming formulation, and this is one of few that focus on just the convex or the real value formulation. However, typically, yes, we could have a mixed integer program in which you could do some sort of decomposition, and there are techniques for kind of maybe solving or kind of relaxing the problem and also solving, okay, you can make it a convex problem, solve it with maybe HHL or something and go back. So there are decomposition techniques, and it's something we've thought about. However, we've also seen that there are a lot of people that do like the actual continuous valued ones as opposed to just the integers. But it depends on, yes, you need to buy fixed holdings or only fixed quantities. You do need the pure integer one, but yes, you could have. Yeah.
So I have a suggestion along those lines. It was sort of a thought I had while you were presenting the paper. One thing you could actually entertain is a horse race between your HHL based methods versus the mixed integer programming approach. Now, I understand that they're a little bit apples and oranges in the sense that you would kind of argue that your weights live on a discrete grid. But it could still be a valuable exercise to see how they compare in terms of portfolio optimization, which I think are kind of addressing the questions that Elton is asking.
Yeah, that definitely would be something interesting to do. And we have heard there are typically a lot of problems in which they do need to use the actual continuous valued versions.
Yes.
In which it consists of just solving these actually very large linear programs. Right. So potentially, yeah, that would be very interesting. I mean, we have also looked into the combinatorial approach, as that's a very popular one you'll see.
Yes. Yeah.
That makes a very good point.
I think we're done for questions, and I don't have anything to add. I really enjoyed it. I think your paper has more to offer than portfolio, obviously, as you said, and I really enjoyed it. I think it's a really great paper. So thank you very much for joining us, and please visit the website. We are continuing this webinar series. I'm kind of signing off for this part of the academic year in terms of financial applications, but please stay tuned for the rest of this webinar series. And I wish all of you a very nice and happy Easter weekend. Thank you, Dylan, for doing this. I really appreciate it.
Thank you so much for having me.